let's talk about well design and construction. I've been in geothermal for decades now, and before that also in the thermal service wells in oil and gas. These are cyclic steam stimulation wells, which incidentally are, I would call, the hottest operating wells, continuously operating wells today would be the cyclic steam stimulation wells that operate at 350 degrees centigrade. So keep that number in mind. Okay, everybody knows what EGS is, so therefore I should not waste time here. Okay, what we're focusing on is what we're going to call next gen or super hot rock, which is 375 degrees C plus. Okay, and here is a very familiar picture from Forge. The idea, what Forge teaches us, not Forge, sorry, this is Fervo, but what Fervo and Forge teach us is that horizontal wells are probably a good way of pairing wells, maximizing the connectivity and maximizing the returns. Okay. So the question I'm going to pose today and try to answer or give you where we are in terms of the answer is how do we design and safely operate wells in super hot rock? That is, how do we maintain well integrity through the service life? One of the things that has been one of my obsessions, like I always say, in geothermal energy has been well integrity. We've done so many RCAs, like Tara said, when people start pointing fingers, somebody needs to find out what happened. We've done so many RCAs, root cause analyses, failure analyses, which is actually tragic because what they're telling you is that these wells did not have adequate integrity. So let's look at how we can design these wells. Let me just summarize some of the key challenges. Okay. In these thermal wells, high temperature wells, you're essentially doing thermal cycling, and therefore you're creating fatigue damage. In the case of super hot rock, you've got much larger cyclic thermal loads, much higher strain localization. I'll explain that later. Cementing is going to be a challenge. Poor cementing will lead to loss of well integrity, and therefore that becomes a challenge in well integrity, not just the cementation. Also in super hot rock, we are potentially going to see high pressures. In hydrothermal and steam stimulation wells, the cyclic steam that I talked about, pressures are very low. So it's very high temperature, but very low pressure. Thermally dominated loading only. Whereas now we will probably also see pressure loading because of the pressures involved in EGS. Okay. Material selection is going to be challenging. Even though the fluid is circulated, it is exposed to formation in an EGS fracture connected formation system. Therefore, we should be worried about material selection as well. Okay. The good thing, of course, is that these things could be managed if you understood the geochemistry and understood how to mitigate against corrosion or scaling. The unique thing about EGS is the inclusion of a stimulation load, and we'll see what the stimulation load does. This is the hydraulic fracturing load. Okay, let's see what's available to us. Let's look at some design philosophies that are prevalent in the industry today. The first is what we call working stress design. Everybody knows this. This is essentially what we do is we take the ratio of the maximum stress to the minimum strength. We stay within the elastic limit, and the safety factor, which is this ratio, should be higher than a prescribed minimum, which we call the design factor. This is the workhorse of design everywhere. All the people here who've done well design should be very familiar with this approach. Most wells are designed using this kind of an idea. Okay. Why does it not work for super hot rock wells? Let's consider a resource at 400 degrees centigrade. Okay, thermal stress is E alpha delta T. E is modulus, alpha is the thermal expansion coefficient, delta T is the temperature change. In the US customary units, where temperature is in degrees Fahrenheit, 200 times delta T is the stress. And the thermal strain, which is what we'll be tracking later, is alpha times delta T. Now, let's assume a cold stimulation load with 80 degrees centigrade flowing temperature at the bottom. So we're now looking at the bottom of the well. Okay. The stress is 115,200 psi tensile alone. On top of this, there is pressure. It's a multi-axial loading, but even just the tensile loading is 115,200 psi approximately. What does that mean? You need a very high-grade material, right? If you want to maintain a safety factor, let us say of 1.25, you have to multiply this number by 1.25. You're suddenly looking at 140 KSI, 150 KSI material. Now let's look at the upper section. Let's say, the shallower section do not see as much delta T during the stimulation load because the shallower sections, the geothermal temperature is not that high. Therefore, their delta T's are low. Now let's produce this well. Same well is producing, let's assume it's at 400 degrees C production temperature. Okay, delta T is higher, stresses are now 136,000 psi. This is happening to the shallower section. So even though the shallower section was safe during the stimulation load, now it is seeing severe stresses. What am I going to do about this? This is the reason why working stress design does not work. And I will show you strain-based systems that we, design philosophies that we use today to design these wells. Okay. The most important one of them is the low cycle fatigue design. Actually, strain-based design is not that new. So the first paper in strain-based design was written by Holliday in 1969. Okay, and he described what is called a Holliday approach, which then later on was, we modified it in many ways and today it's called the modified Holliday approach, and it's often used for the design of steam stimulation wells. The most sophisticated version of these methods is what I'm showing you here now. It's called the low cycle fatigue design approach. It is used now in hydrothermal wells and even cyclic steam stimulation wells. We conduct true stress, true strain tests of the material, and we obtain the stress strain curve, true stress, true strain curve, which is a power law curve. The N and K are usually called the Ramberg-Osgood parameters, and this is called the Ramberg-Osgood equation. Okay. Then once we know the starting point, we will know we are going to work in strain, not in stress. Okay. So once we know the starting strain, we calculate the strain increment and move along the Ramberg-Osgood curve according to the strain increment using what is known as the Masing hypothesis, which is shown here. It essentially, what it says is there are some materials which exhibit symmetry across the y-axis, okay, in the hysteresis loop. And this is called the Masing hypothesis. So we are going to use that as well. Then what we will do is we will accumulate the fatigue damage caused by these cycles, that is the plastic strain increment, in a parameter called DFDI. DFDI is ductile failure damage indicator. Again, this is not very new. In the 1990s, it was introduced, and it is used heavily in pipeline design, okay, for large displacements. So what we do here is we accumulate the damage. This will go to 1 ultimately, and when it goes to 1, we predict ductile failure or fatigue failure. Okay, so in design, we will leave it at 0.7. One other innovation that we will use is what is called critical strain. When you look at DFDI in literature, you will find them right here, epsilon F or failure strain. Okay, but we are stopping at critical strain. What is critical strain? It is the strain at which microvoids coalesce within the material. It's a micromechanical behavior, and it shows up as the second knee in your stress strain curve. Okay, it's a material property. It's also been discussed in literature quite a lot. Okay, so the DFDI also needs stresses, but of course, if I know the strain, I can convert it to stress, right? Using this equation here. So I can calculate stress from strain and vice versa. What do we do about the connections? This is very good for the pipe body. What about the connections? For connections, what we will do is first of all, a connection is a structure. It is not like a pipe body, right? There are some structural components within the connection so that the stress distribution and the strain distribution within the connection is not uniform. In fact, the maximum strain in the connection will be higher, augmented compared to the strain in the pipe body for a given delta T. Okay, so what we do is we build a model for the connection in FEA, and we simulate the cyclic loading, and then we look at the ratio of the DFDI in the connection to the DFDI in the pipe body, and we call it a strain localization factor. Here is an example. What this is for a buttress connection. You got all the details here. Plus minus 0.5% cyclic strain is not unreasonable. It's yield strain. We are plasticizing. So we go, essentially what it's telling you, let's look at 10. At the end of 10 cycles, it's about 2.8 to 3, right? What that means is that the damage in the connection is 2.8 times the damage in the pipe for the same delta T. This is very important to know because connections are probably where we'll see the failures. Okay. Now to understand what we are doing to these materials, to construct a basis of design for super hot rock wells, we first need to understand the stress strain behavior in geothermal wells. What I'm showing you here is the stress strain curve. The green, this is the stress epsilon strain axis. This is the stress axis. This green curve is the Ramberg-Osgood curve for that material, stress strain curve. Let's see what we're doing. We're starting, let us say, from point 0. Okay, that is the starting point when I install the casing. Now the first thing I'm going to do is heat the well. So I will go down this line, I'll plasticize and reach a point 1. Okay, that is my producing period. Now I cool it down. I shut it in for whatever reason, right? Then I come back through a different curve and end up at point 2. So you can see I started with 0 tension, but when I finished one cycle even, my tension is now close to yield. Okay, and as I keep going around, this hysteresis loop will continue, eventually stabilize. There are some details here that we need to pay attention to, such as strain hardening, which is shown there. For example, K55 at 350 degrees C, after 30 cycles, has a yield strength of 77 KSI. So it's being heat treated in the well. Okay, so strain hardening can happen. Boschinger effect will also happen there. Thermal relaxation will happen in the bottom. So all of these features have to be taken into account. Nevertheless, for illustration purposes, what we have is a hysteresis curve. Okay, the area inside the hysteresis loop is proportional to fatigue damage. So essentially, accumulating this area is essentially what we are doing in most of our fatigue design strategies. Okay, so let's watch that, the size of that area. Now, in geothermal, hydrothermal wells, there is a load case called quench load, which is analogous to stimulation, except that it is not high pressure. So let's apply that quench load and see what we're doing to the well. We start again from 0. We are at 1, right? We're producing. You quench when you produce. Therefore, at this point, you're applying a quench load. So 1 to 5 is the quench load movement. And we normally design the quench load to be within the elastic limit. We will use working stress design for the quench load. It's an important strategy which we will borrow when we go to super hot rock. Okay. Then after the quench is over, you put the well back into production. You now follow another loop. Okay. Now you go 5, 6, 7. This is the loop that you're going around. What do we see? We see two things. One, the area is about the same. That means my quench load did not add any additional damage to the well. Second, I'm seeing movement to the left. The left is compressive. Compressive is good when you're thinking about fatigue. So quench is not such a bad thing. It is not hurting me so much. Now let's look at a super hot rock well. In a super hot rock well, if you're only producing, then this is how it would look. This was the hydrothermal well. Super hot rock, maybe you go a little bit more and you execute these loops. Okay, but let us stick with this loop and see what we're doing to the well. Let us say this is my damage if all I do is produce and nothing else in this well. But the first thing I'm going to do is stimulate, right? So I go from some initial point to 1, that is my stimulation load. We will use working stress design for stimulation load, maybe use advanced techniques, reliability-based design that will take me up further into that curve. I finished my stimulation, I unloaded. Now I'm at point number 3. So my production starts not from I or not from 0, but point 3. So when I complete my production loop, you see that the area of the curve, the hysteresis loop is larger. Okay, so the fact that I'm stimulating first has a price. And that price is additional fatigue damage. Okay, of course, once you quantify this, you can take all this into account. Fortunately, the demand is not very high. Maybe 30 cycles. Most geothermal, hydrothermal wells that we design to maybe 30 to 50 cycles maximum. Okay, whereas a cyclic steam stimulation well, maybe 150 cycles lifetime. So the demand is not high, but you have to know this fatigue. Okay, now let us say, oh, I want to refracture the well. Someday somebody is going to say, I have a super hot rock well, I've produced it for a while, now I want to refrac it. Okay, let's refrac this well. We started again from this point, we went around here, we are now at point number 5, right? When we shut in. Okay, we've reached point number 5. It's cold, shut-in period. We are going to refract from there, not from here. When we fract from here. When we refract, we're refracting from there. So all my movement is in the plastic region. My movement is causing tensile plastic strain. The refract stimulation load is causing tensile plastic strain, which when I complete the loop has made it even bigger. Right? I'm moving up to here now and coming back down the loop. So the fatigue damage will increase beyond the refract. So these are some of the concepts we need to keep in mind when we try to construct a basis of design. Okay. But one thing we've already noticed is that the lower section of the tubulars is dictated by tension, stimulation load, tension. The shallower sections of the well are dictated by thermal and temperature loading, right? So can I design this in such a way that I satisfy working stress design for the stimulation load for the lower section, so that the lower section, which will not see a high delta T during production, remains elastic throughout its entire life, and the upper section I will design using low cycle fatigue. So you're now looking at the well in two parts and designing them individually. Okay. The other thing that I will be talking about that a little bit more later. So let me carry on. How am I doing on time? Okay. So we are trying to find the depth at which you can go from low cycle fatigue to working stress design and select our grades accordingly. A lower grade tubular for the upper section, a higher grade tubular for the lower section. Remember one thing, okay? If you take one thing only away from this discussion, ductility is very important. It is emphasized by all structural codes. It is being emphasized by me that if you have two choices, always move in the direction of ductility, higher ductility, not higher strength. Okay, so that is what we're trying to do by using lower grade materials in shallow. Okay, why is well design important? Look, Superhot rock is not so first of a kind. It has been done many times, as you can see there, and the references below. Okay, in all the cases, what they have said is that the produced fluid was highly corrosive and hostile. In all cases, damage was reported. Okay, and this particular paper, Kruzewski and Wittig, the casing program is the most crucial feature that influences successful drilling operations and the longevity of the future geothermal fluid production. The kind of words we hear when we read these papers, review papers and discussion papers, we hear words like casing collapse, connection failure, corrosion, erosion. Okay, these are the kind of things we even hear about wellhead failures. Okay, so no matter the resource, what it appears is that in Superhot rock, it is the well that gives up first, robbing us of the opportunity to investigate the resource. Okay, prematurely taking it away from us. That's what we need to address. When I talk about well construction design, what I want is let the well live so I can look at the resource. Okay, IDDP, this is Iceland, the cradle of geothermal energy. So, and IDDP, they're the only ones bold enough to do these kinds of projects. So, as we know, in both cases, there were failures. So let's look at what happened here. Obviously, this is a very quick review. One of the papers that I used in this was Ingerson's paper. And I think he's here in this room today. Somewhere. Okay. Thank you, Christian. Yeah. So in IDDP1, the production casing they used was 9 5/8 inch 5350 K55 ductile material with hydril 563 connections. The well failed. Failures were reported primarily in the connections. In the paper, they called out the potential cause of failure was a quench load. This is a hydrothermal, but it is still Superhot rock. Okay. So the question today we will ask is, could there have been a connection strain localization that was high? Is this connection, what is the strain localization for this connection? Okay, and did the connection fatigue and fail? This is a question. I don't know, but I'm just raising the question here. IDDP2, look at this. There has been a radical change in design. In IDDP2, 9 7/8 inch, 62.8 pound per foot T95 with geocon connections. Geocon is a very popular connection used in hydrothermal wells in the Far East and also in New Zealand. So this is not an unusual choice. But then they reported a collapse-like failure at about 2,300 meters depth. At the same depth, they also reported poor cementing. The intermediate casing, I've given you the details here because I'm asking what could be the reason for this. Was it an APB collapse? Was it a cold collapse? Was it inelastic buckling? I'm going to talk about these in a second, what these are. But I don't know because unfortunately the basis of design for these wells has not been reported in the literature. So I don't know exactly how these wells were designed. What was the logic? What was the basis of design for them? We don't know. All we know is post facto, there was a failure. That's all, okay? So basis of design, how do we put this together? Okay, high pressure load, this is a proposed basis of design, okay? High pressure, low temperature loads will be subjected to working stress design and if required, reliability based design, okay? Thermally dominated loads will be subjected to low cycle fatigue design. Okay, so you will apply both design methods. Depending upon the load case, you're applying different design methods to see if the well will survive or not. Okay, you need thermal analysis for a number of load cases, including transient startup and shutdown, and some kind of a discharge or blowout load case, because even though this is EGS, that could happen. If you lose containment or if you lose something, you could still have some discharge or blowout. Okay, then we have to worry about APB. What is APB design? In pipe section, IDDP2, the failure was not in the pipe section. That's why I'm not sure it could be APB collapse. But in the pipe section, if there is a trap mud pocket, as the temperature increases, the pressure in this mud pocket increases, creating a collapse load on the inner pipe, which is a production pipe, it fails. Okay, you can avoid it with good cementing, but you can also use clever design. What you can do is you can design the next outer string to have a higher probability of rupture before the inner string will collapse, thereby directing the failure outwards. This philosophy is used in oil and gas wells, deep water wells, for the exact same load, the APB load. What is cold collapse? Recall I showed you how when I cool down I come to very high tension, and now when I quench it, the temperature is also falling. It also creates a collapse load. Because I'm at high tension and associating that with collapse, my collapse strength is much lower. This phenomenon was called cold collapse by Maruyama et al. In the 90s. It was the first people to describe this problem. And you have to have a design basis for cold collapse as well. And one of the papers that I referred to here, not this one, this one. There is a lot of discussion. There's more discussion about collapse in there. The third thing is inelastic buckling. If cement is poor over some length, but not very long length, let's say 3 feet, 5 feet, that kind of length, there is poor cement and there is unsupported section. Even if there is no mud pocket, when delta T happens, that section will buckle, but not elastically, inelastically, which means it will go beyond its elastic limits and it'll take a shape, a bent shape with plastic strain in it. Okay, this is dangerous because when you cool it, you could just break it apart, right? Exactly at that dog bone. Okay, material selection is also very important. I don't think I can finish material selection here today for the time you've given me. Okay, so casing wear needs to be looked at, wellhead movement and force distribution, because we might end up having to use conventional wellheads rather than just geothermal wellheads, because hydrothermal, geothermal wells, the wellheads were rather forgiving because each string was allowed to expand on its own. We may not have that luxury here because we're going to do a stimulation load. Okay, and remember one thing, that outer casings are also subject to temperature change. So don't just look at your production casing, look at your outer strings as well. Okay, so this I'm illustrating thermally managed installation. What I'm showing you here are various temperature profiles for various load scenarios. This black curve is undisturbed geothermal temperature profile. Okay, this is producing temperature profile, but let's look at the undisturbed, it's not even super hot rock, but let's look at the undisturbed temperature profile. This is usually considered the installation temperature of the casing. But what I'm showing you in addition is the temperature profile after you waited on cement. It is quite a bit colder than this, right? Okay, this just happened. But what if I can deliberately reduce the installation temperature of these casings? What will I do? Rather than have such a high delta T during stimulation, this is the stimulation temperature profile, I have a much smaller delta T in tension. I now pick up a more greater delta T in temperature, but I could manage this in such a way that I gain on this side without getting hurt on the other side. Okay, so that could be something that we can use. We can use it also for liners. Okay, leave you with some thoughts on well construction. Ductility is more important than strength. Modern well-designed construction ideas will have to be used. Low cycle fatigue, reliability-based design. These are the kind of ideas we need to use. No longer the working stress design type thinking. Okay. Material properties can be significantly altered at temperatures approaching 450 C. These are not well understood currently. Our maximum is 350 C, as I said. So this is something that we need to also do. Cement design and cementing are critical. Okay, I already mentioned that the material selection, one advantage of EGS is that the flow is in a closed loop, so I can actually control what's going into my injector and thereby mitigate corrosion, only if I understand the geochemistry. I think Tony may or may not have mentioned this, but reverse cementing will have to be considered because cement is going to be quite critical. Corrosion is a very serious threat. How do you design for corrosion? Let me take you to an example. Okay, you design for corrosion. First of all, you need to know the chemistry of the fluid that you're producing, from which then you will figure out where the phase changes are occurring. Okay, this is the single phase liquid. This is the water vapor breakout region, and it's varying in depth because it depends on the well, right? So you're doing a design check for corrosion. And this is the vaporized section where you got steam now. For each of those, you look at the volume of the aqueous phase, which then you can look at the chloride concentration, which then you can use in a model like OLI to calculate the corrosion rates. These corrosion rates must be taken into account in your design, right? Because they are happening. For example, in this example that I'm showing you here, the average life is 19.2 years. Okay, so even if there are no other loads, corrosion alone is going to kill your well in 19.2 years. So you need to know what corrosion is doing to you. Brittle failure is also a threat. Okay, a good example is the pictures I'm about to show you. 1 minute, yeah. The pictures I'm about to show you, which is a geothermal well. It was an EGS well in Habanero. All of you are familiar with Habanero. We did quite a bit of work there several years ago. Okay, it was the well that failed was a geothermal well with 150 KSI grade material used as production casing. This is an important point. Why did they end up with 150 KSI? We just spent so much time talking about ductility as being our friend, and here these guys went to 150 KSI. Why? Because they used working stress design. That was the only way they could satisfy their factors of safety. Okay, then we looked at what happened to them. It was brittle failure of casing, and here are some pictures. This is what happened to them. Okay. And this happened at high pH, not low pH. Normally we worry about brittle failure at low pH. This happened at high pH. So it's called caustic cracking. Okay. It happens at high temperature and high pH, which is both conditions we can have in our wells. Okay. So don't forget a few caveats. Don't forget the outer strings. You need to worry about APB. You need to worry about collapse. Most failures in geothermal wells, incidentally, you will see will be collapse-like. Okay, so that is something that we need to worry about. Where is the critical considerations? Because these could be horizontal wells, directional wells. So this where is going to happen at the beginning. Take it into account in your design. Okay, of course, I have conveniently ignored how to perform the multi-stage hydraulic fracturing operations. Hopefully Trenton, who comes after me, will dig a little. Trenton is here, so we'll dig a little bit more into that. Okay, that is a bigger problem in my opinion, but still. Okay, so what are the open problems? Material properties and response at temperatures above 350. At 350 itself, we're heat treating the material. At 450, think about it. Okay, we need to understand the geochemistry of the flow. We need to understand how we can manage the circulating fluid. This has to be done both in modeling as well as in the laboratory. Okay, which is the testing of scaling and mitigation techniques. And impact of, thank you, Tony, for this, impact of shallow formation heat up on aquifers and groundwater flows, something we don't think about. If there is no water in a hot, dry rock, but up there could be a shallow water flow, which somebody may require you to protect. So therefore, you have to worry about what you're doing to that. Okay. The fatigue, the other thing that worries me, even though DFDI is multi-axial, it worries me how will multi-axial fatigue behave. Okay. Inelastic I've talked about. Strain amplitudes in connections will be higher. We need to worry about connection selection a lot more now than even at 350 degrees C. Okay. So selection of the right connection and designing the well such that the connection fatigue failure, the number of cycles to fatigue failure is much greater than what I actually need during my operations, or learn how to manage my operations such that I'm staying within this limit. Okay. Cement studies are needed, and finally high temperature proppants that will not break the bank. Okay. So in conclusion, I think we've learned a lot. Tara mentioned shale, but I'm also adding thermal EOR and hydrothermal and HPHT. All of these have taught us a lot. We can apply all these, but there are many challenges, as I've discussed, at least as far as well construction is concerned. But despite these, I think that we can construct and operate wells at temperatures at less than or equal to 350 C, because that's already been done. Okay. The problem is when we go beyond 350 degrees C, and in this I agree with Tony that what we need are engineering breakthroughs, not scientific breakthroughs. So it is simply engineering, dogged, plain old common sense, persistent engineering is what we need. Most of the science is there. That's all I had to say. Thank you very much.
All right, it is Q&A. I will remind you that we do make these reports available online. So for those of you like me that cannot do the differential equation in your head live, you can follow the QR codes. You can also go to our website and find the details of this report. It will be available shortly. Currently, we have 3 of the 5 technology verticals available in their full 60 to 100 page form. Enjoy.
Yes, and I wanted to add to that. In this report, what I did not show here, as it is, I almost ran out of time. In fact, I ran out of time. She's just kind. But in the report, I also go through some examples, numerical examples, so you can see what happens as you increase the temperature. So I start at 250 and go all the way to 400 to show you what's happening to us and what we're doing to the material. Please go ahead, Tara.
All right, I'll take questions. All right, Tony.
So, Suri, through doing all this operation, is taking the temperature of the wellbore down before we run each casing and cement job, is that helping us or hindering us?
It would help us for the stimulation load.
Right.
So you do it selectively. You lower the temperature below. Fortunately for us, the circulating temperature profile looks exactly like that. The lower part of the hole is cooled, the upper part of the hole is heated, right?
Yes, exactly.
So by playing around with that, you could make sure that the lower part of the hole, when the casing is installed at a temperature colder than geothermal. That buys me something.
Brilliant.
Because now I don't have to use V150s and all that.
Thank you. Torsten?
Thank you. So you keep talking about EGS here, and I'm interested in AGS or closed loop as well. If you have any opinion on, seemingly that would create less stress if we don't have to engineer the reservoir. Any thoughts on non-EGS Superhot rock?
Oh, absolutely. I think that's if it works, it's a very good idea, because if you're truly closed loop, you bought yourself out of one big problem, which is corrosion, scaling, precipitation, etc. Okay, that's immediately gone. A lot of the guys who are doing hydrothermal report that all the time. EGS comes somewhere in between. As far as temperature is concerned and the stresses are concerned, The stimulation load is if it is excluded from my load set because you're not going to stimulate these wells at all, then you can design them as pure hydrothermal wells. Even so, if your temperature exceeds 350 degrees C, you still have to go through the low cycle fatigue to make sure that your cycles are within the limit.
We'll take one more question. Oh, goodness, then it'll be mine. Sorry, earlier you pulled me aside and pointed out one of the major gaps that we have is actually bench scale and laboratory testing at these temperatures. I wonder if, in the context of the equipment innovations needed for casing and completions, do you believe that what is needed at scale for testing, and would you always prefer in-field testing? What equipment do you think is appropriate for laboratory?
Well, the laboratories, first of all, to add to what you just said, Tara, what we don't have is a lab that can routinely conduct tests at 450 degrees C plus, whatever test they might be. If I had a lab like that, what kind of tests would I do? I would do all my geochemistry tests there. I would do all my scaling control tests there. Okay. In order to do tests of the pipe body or the connections, I will need full scale testing. There is a protocol called ISO 12835 that governs the connection selection for thermal service wells. It's also used by geothermal people, hydrothermal people. Okay, but that ends at 350 C. There they physically cycle the pipe at 350 C with the connection in it and design the test in such a way that the thermal cycling is causing stress cycling and strain cycling in the pipe body and the connection. Such a lab doesn't exist. Although I made a very similar presentation just last week in Houston, and some of the connection manufacturers walked up to me and said that they would like to share some of the results that they're getting. So I'm hoping that somebody has done a 400C test, which means they probably have some kit for it. So that's one full-scale test I would do.
Thank you. Sorry, I appreciate it. I am going to quote what he said earlier, which is, let's let the well live so we can understand the resource. And with that, I'm going to give it to Trenton so he can talk about the resource.